Rowlett from Chalmers University of Technology, who will talk about isospectrality and moduli spaces.
Okay, so thank you so much for the invitation. It's really a great pleasure to be here. It's an inspiring place, and the lineup is full of inspiring talks, and it's really a pleasure to be the first. So before I get into it, all questions are good questions, and all answers are good answers. We can always learn something. So please feel free to interrupt me at any time with a question. And if I pose a question, I hope some of you will feel confident to propose an answer. So my talk is maybe a sort of nice warm-up to get into the topic. Because I have planned it, fully expecting that everyone can stay with me for the whole time. I think you can all handle the entire content. Okay, so isospectrality on moduli spaces. So let's start from the beginning with isospectrality. Have you all heard the question, can one hear the shape of a drum?
Yes.
Have you heard it maybe one too many times? I think everyone here knows the answer. Or do you? Right? Because the answer to the question is going to depend, we're mathematicians. So what do we mean by a drum? What do we mean by hear? We could mean different things. So as a warm-up, both for my talk and everything that follows, let's solve something together. So we are looking for functions such that the second, so this is just a function of one variable, and we want the second derivative to be a constant times the function. And I write it this way because of reasons probably some of you know. And then I'm going to impose these further conditions. So this lambda is a constant. A priori, it could be in the complex plane. And then I impose these conditions. Okay. So this is my, in this case, differential equation, and this is the boundary conditions. Okay, so ready, set, solve. Find all the f's, please, and find all the lambdas. Go ahead. It's a good opportunity to talk to your neighbors if you haven't met them yet. Just take a minute, it's a warm-up. You can do it. I know you can do it. I'm about to teach this to my second-year students. I believe in you.
Actually, can I ask a question?
Of course.
I don't understand the third condition. Shouldn't it be implied by the second?
No, not necessarily. Exactly. So for this to be what's called a regular Sturm-Liouville problem, we need both. Also, though, we could get, I saw somebody nodding at me, you could get some sort of icky solutions if you don't impose this.
So I always
The things that are going to come to your mind, once you have this, this will follow. But you could cook up other things. It's fine. Small. That would be yucky. So let's take both.
I'm still sorry, I'm confused. So you have that your function is periodic, period L?
Yeah.
So,
And its first derivative also should be. So I don't want any wonkiness happening with the first derivative. Yeah?
oh, so you're okay.
Does this make sense?
I mean, so you're not assuming f to be differentiable, continuously differentiable.
I'm assuming that all of these things make sense. Weakly differentiable,
I'm
H1.
saying if you differentiate the first boundary condition, you get the second one, right? That's your problem.
Yes, that's precisely my problem.
Right, unless something strange happens with the derivative at the boundary point. And that's what I'm saying I don't want to allow.
There's no boundary.
Well, the way I wrote it, there is. But anyways, can we find the lambdas and the f's?
Do you mean a function on an interval, or is it a periodic function on R? Because if it's a periodic function on R, there's no boundary, right?
Sure.
Sine, cosine, any real number bigger than 0.
Pardon?
Sine, cosine, and any real number greater than 0.
Okay, so not just, what's the argument of the sine or the cosine?
Oh,
Like, which specific lambdas do we find here?
Negative ones.
Really?
Positive ones.
Exactly. And what are they?
2 pi over L squared.
Squared. Thank you. 2 pi over L squared. Just that, or?
Plus and minus. No.
I hear that. What's K?
Sorry, any
Okay. Here we go. See, it's a warm-up. So you have a constant function. And of course, for this to be a non-trivial problem, we don't allow the zero function. So, lambda is 0, constant functions satisfy everything, yes? Okay, the other values are what I will call lambda k, 4 pi squared k squared over L squared, with f plus minus k, so they have 2 e to the 2 pi I k x over L. Yes? So if you, each eigenvalue has 2 eigenfunctions, and if you add or subtract them and multiply by, or divide by 2 or 2i, then you get sines and cosines, right?
Plus minus in the exponent as well, right?
Oh, yes, thank you. Exactly. Yes. Okay. So isospectrality means having the same spectrum. So all of these eigenvalues give us the spectrum. Isospectrality, the first word in the talk, means having the same spectrum. So, now, geometrically, some people might have recognized that this is the Laplace eigenvalue problem for a one-dimensional flat torus, or a circle, same thing. Okay, so let's think about now moduli spaces, the second term in the talk. On the moduli space of one-dimensional flat tori, what does isospectrality tell us? So in other words, if you know the spectrum of a one-dimensional flat torus, do you know something about the one-dimensional flat torus? You know everything about it, because the only thing that distinguishes a one-dimensional flat torus is this number L here. So, that gets me into moduli spaces. And the first type of moduli spaces will be moduli spaces of flat tori. Okay, so one way to view the moduli space of flat tori is like this. So let me explain. In n-dimensional Euclidean space, is a quotient. So, sorry. A flat torus is defined as a quotient by a full rank lattice. And so full rank lattice in Rn is a set of the form so it's basically all integer linear combinations of a set of linearly independent vectors. That's what this means. And so that's where our B in GLN-R comes from. So one way of expressing this is you take an invertible n by n matrix.
This is the set of lattices.
Pardon?
What you wrote is
Oh,
the set
sorry,
of
sorry, sorry.
lattices. For
Sorry.
a given B is a lattice.
It's this set. For some B. Yes. So, a lattice is a set of the form integer linear combinations of n linearly independent vectors, right? So that's where this comes from, because this is what's called a basis matrix for the lattice. But then if you were to multiply that basis matrix on the right with an element of GLNZ, it's the same set. Okay. So basically, these basis matrices are only unique up to multiplication on the right by elements of GLN Z. But then if we take an orthogonal transformation of Euclidean space over here, i.e. multiply on the left, it's basically the same shape lattice. It's just sitting in space in a different way. So I can identify the moduli space of flat tori so a flat torus is one of these lattices, the quotient of, call this gamma b, Euclidean space by such a flat torus. And so when I say moduli space, I'm viewing them as the same flat torus when they're, this would mean as Riemannian manifolds, they're isometric. Okay? Okay. So now let me introduce the definition. Flat n is the supremum of the number of elements of Mn that are distinct, it's a little bit redundant, that are isospectral. Okay, so what's Mn? This is my moduli space of flat tori in n dimensions. So basically we're looking at how many flat tori in a given dimension can have the same spectrum. So what are some values of this flat n for different n? For example, what is flat 1?
normalized the volume?
No. We have not.
Yes. Once you know the isospectral, you know the volumes. That's all.
Of course. So anything that is,
May
so
as
any
well assume
collection
the
of
volume
these,
is-
any collection of these would all have the same volume, right? So in one dimension,
One.
what are some other values of flat n?
That's infinity.
8 is the first time I know this. Dimension 8. That's more.
So let's put some dots in the middle. So flat 8, you're saying it's greater than 1, right?
16 for sure, I know.
Okay, so I'll just put some dots here. So flat 16, do we actually know its value?
More than one.
It's more than 1. It's greater than or equal to 2.
But
Yes?
if you have two with the same volume that are isospectral, and you multiply each one, and you change the volume of each of it, it will still be isospectral.
Pardon?
If you take two isospectral sets, they have the same volume. And now each toroid, you multiply it by a fixed constant.
Yes, flat 2 still stays 2.
The definition misses the part where you say in one class, in one equivalence class. Right? It's the supremum in one.
Oh, okay.
To each other.
Mutually. Mutually. So how many can share one spectrum?
So it's a BNP. Yeah, okay, I get it.
Yeah. How many can share one spectrum? I think that's
Okay,
what I was meaning.
okay.
Yeah. So we know, how do we know that flat 16 is greater than or equal to 2?
Because Milner.
Because of Milner, exactly. So this is a theorem from Milner in 1961. Okay, so he constructed two flat tori that are isospectral because of reasons from analytic number theory. Proving isospectrality isn't necessarily the easiest thing in the world, but in that case it's quick. And they're very clearly not isometric because one is a product and the other is irreducible. So it could not be expressed as a product. So therefore, geometrically, they cannot be isometric. Okay, but that just tells us it's greater than or equal to 2. It doesn't tell us it's equal to 2. What is it equal to? Nobody knows. Okay, so let's start closing the gap. What do we think flat 2 might be? 1. Yes. So somewhere it changes. This is a little bit harder to prove, but I think if you took the afternoon, like one of the breaks, you could do it. It's not that bad. Like it's less than a page. No. This one you can do directly with the fact that in 2 dimensions you have very nice bases for lattices consisting of like shortest vectors. Things get very strange as the dimension goes higher. So that's not always true. But in low dimensions you have a very nice basis for your lattice, and so you can kind of quickly get to this. So does anyone know where it changes? We have 1, 1, at least 2. So I'm not surprised that no one knows where it changes because this is published in a very obscure article that never mentions any of the following words. Torus, tori, spectrum, eigenvalue, Laplace, Laplacian, isospectral, isometric. None of those words are anywhere in the article. So if you were looking for the answer to this problem, it would be a little bit tricky to understand that that was the article that contained it. those words are contained in the thesis, the PhD thesis that led to the article, aber sie sind alles auf Deutsch. So, dann musste man Deutsch lesen können und auch diese Doktorarbeit. You'd have to be able to know German, and you'd have to be able to fetch the PhD thesis from the University of Bonn's library. Which, I don't know how easy that is from abroad. In Sweden, we could do that. But yeah. So, the tipping point, I'll express it as a theorem. It's by Alexander Schiemann from about 1991. And it says that flat n is 1 if and only if n is less than or equal to 3. Flat n is greater than or equal to 2 for n greater than or equal to 4. So 3 is the tipping point. Now, I will not give you as a homework for the afternoon the proof of this fact for n is 3. Why will I not give you that proof? Well, because to date, no one has been able to prove it by hand, for starters. And the algorithm involved a bit challenging.
What was his answer?
I think it was Wallman? I think it may have been Wallman. No, it's correct. And actually, together with some of my students, we have been able to redo the algorithm and carry out the proof again on modern computers. So the proof is correct, but no one knows how to do it without the assistance of a computer.
You certified in some sense?
Pardon?
You certified the algorithm?
Yes, we did. This is actually kind of funny. So when my student was working on this algorithm, this was just a few years ago, and he was struggling to get it to run in a decent amount of time. And he asked me, did Schiemann have access to some sort of special computer? And I just about died, because I was like, dude, Schiemann's computers were weaker than your phone. So no. And the problem was that a certain calculation was being redone over and over again sort of every time. So there was some redundancy in my student's code, and then he fixed it, and then it would run. It was just funny to think about the computing power available in 1991 versus now. Yes?
So do we know if the n is always finite?
Yes, thank you, that's a really good question. So that's another theorem. And another one that's also very difficult to find by another German PhD student. So this is from Yuriko Suabiers. And it's around the same time. And it says that flat n is finite for every n. And you can extract an upper bound from it, but it's really, 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 really bad. And it's not really easy to do because, again, you have to go through this. This obscure German PhD thesis is found in Göttingen. And so what Schiemann did is Schiemann proved that flat 3 is 1, and then he found the first example of a pair of isospectral non-isometric 4-dimensional flat tori. So that tells us flat n is greater than or equal to 2 for any n greater than or equal to 4. That actually gives us a larger lower bound here. Can you see how to do that? Exactly. You make silly combinatorial products. So then once you know flat 4 is 2, at least 2, and you have examples, then you take products and you can get more and more as the dimension goes higher. So this tells us that flat n goes to infinity as n goes to infinity. And it actually grows like super exponentially. But it is always finite. So,
Do you know if it grows faster than what you would expect from the number of divisors?
Oh, for sure. So divided with into the epsilon. So it's super exponential.
yeah,
Like can you does it go much faster than the city combinatorics that you can get by products?
the estimates that we have are just the silly combinatorics.
The lower one.
And something else that I'm going to get to now, which is a theorem for us. So actually, before I get to the theorem, then I'll put this here, an open question. What is flat n for n greater than or equal to 4? And I'll give you a conjecture. Which is, we think flat 4 is 2, and flat 5 is 2. I'll explain the reasons why we think that. And before that, I'll give you a theorem. So this is together with Gustav Moduli, my current PhD student, and Felix Bedell, my former master's student, who now works for the Swedish Defense Research Agency, doing important things for Sweden. And it says the following. Flat 6 is at least 3. So we have ideas for how to generalize Schemann's proof, prove this in dimension 4. We're more confident about this part of the conjecture than that one. But then, basically, we got curious because when you look in the literature, you're always seeing pairs. Pairs in 16 dimensions. Then somebody obtained a pair in 12 dimensions. And then in 8. And then in 6, and then in 4. So we thought, triplet, anybody? Let's see if we can find one. And we did. One of the interesting things about our triplet is they're isospectral, non-isometric, of course, and they're all irreducible. So none of them decomposes as a product. Because one of the standard types of examples is you have this one's a product, that one's not, and then your isometry check is sort of done very easily. If that's not the case, then you have to do some work to show that things are not isometric. Yes?
Are there things that have isospectral mates isolated in the moduli space? Do we know that? Or could
I
there
know
be
that they are
families-
sort of rare in the moduli space.
Sorry, but could there be a family that all had an isospectral pair, some other family elsewhere?
In 4 dimensions, you have a 1-parameter family of pairs. So that happens in 4 dimensions. It's still pairs, but yeah, you do have like a 1-parameter family of pairs in the moduli space. There's this paper by Scott Wolpert that characterizes sort of how rare this phenomenon is from a certain more like measure theoretic sense in the moduli space of flat tori. Like it's like a set of measure 0 where this happens. So how do we do this? Yes, exactly. So that example was conjectured by Conway and Sloan in the early 90s, and then it was proven. So Conway and Sloan conjectured that there exists this whole 1-parameter family of 4-dimensional isospectral non-isometric flat tori. And they didn't prove it. It was proven by Servino and Hein in around 2010. So it actually took some time to prove that conjecture of Conway and Sloan, but now it's known to be a fact. Pardon?
The one parameter family, is it analytic?
I mean, there's basically, it's an analytic. What do we, does it depend analytically on the parameter?
Yeah.
Yes, it does. Yes. Okay. So how do we do this? I think this will be kind of fun. So, just give you some idea about it. So we use something called linear codes. So we take integers modulo some value, and it doesn't have to be prime. And this additive subgroup. And we look at these, so linear codes are defined to be subgroups of Z mod QZN. The elements of a code are called code words. So as a first question, how many codes are in here? Okay, the exact number is actually a bit tricky, especially when Q is not prime. That's something that one of my students is working on, a formula for this, and she came up with, in fact, an expression that's lovely and horrendous at the same time. When Q is prime, this is sort of feasible, but anyways, it's a big number depending on Q and N, but it is finite, right? And everything in here, so there's finitely many, and they each can be turned into lattices. So this is how that works. So if you have a set of generators, so let's say there's C1 to CK, then if I take this matrix, I will get a full rank lattice in Rn, or in Zn. It's going to be an integer lattice. So I basically take the generators, and then I stack on Q times the n by n identity matrix, and then I look at all points in Rn that are this multiplied by Zn plus k. So all integer linear combinations of these columns. And that gives you a full rank lattice, because of course lattices are discrete additive subgroups of Rn. So here's where the proof comes in. So for each n and each q, there's finitely many of these, right? So we can look for codes that are going to give rise to isospectral but not isometric lattices, or flat tori. So lattices that, when you took the quotient, Rn, would give you isospectral, not isometric flat tori. So in essence, basically, you can write a program to search. And one of the important ingredients is the following theorem. So if two codes have the same weight distribution, then the flat tori corresponding to the lattices obtained by those codes are isospectral. So this is not due to us. It was maybe first proven by Conway and Sloan. Yes, and I'll tell you what a weight distribution is.
Just to make sure, this construction, the way that you did it, is to make sure that multiplication by the right by GL and C doesn't change it, so that it's unique. If I choose the C1 to CK elements in this Z mod QZ to the N,
Right.
and I multiply this matrix from the right by GL and Z, because of the QI identity, and the C mod QZ, and I'm still in the same.
Yeah, it makes it independent of the choice of generators.
Perfect. So that's so.
Yeah.
So this kills the multiplicity from this kills the right division.
Yeah.
Thank you.
So this weight distribution means two codes have the same weight distribution if they have the same number of code words. And if you can put the code words, you can pair them up so that each pair has like the same entries. They're just permuted. That's what that means. Yes?
Is it correct that this is a covering for smaller torus?
That your example here is a covering of so. Oh no, it would be multiplicative. Okay, I will think. We'll discuss.
So if you have an efficient algorithm that takes the codes and groups them into codes that have the same weight distribution, then you know that those codes correspond to isospectral flat tori.
But what is the weight distribution?
Again, so having the same weight distribution, I don't know if the weight distribution itself has a definition. The definition is for having the same. And to have the same weight distribution, you have to have the same number of code words. So the same number of elements in your subgroups. And then you have to be able to pair them up so that in each pair, these are vectors, right? So in each pair, the vectors have all the same entries, they're just permuted. They're just permutations of each other. And if that is true, then the corresponding flat tori you'll get are guaranteed to be isospectral. It's not the easiest thing to see how the proof works, but it's in Conway and Sloan's book. Did you have a question? You had your hand. Okay. But I can also take them afterwards. So start with n is 4. And then maybe go up to 5 and go up to 6. And compute for, q is 2, 3, 4, 5, just marching up the integers, the codes, in Z mod QZN, with the same weight distribution. So you start by computing the codes and counting how many code words they have, because to have the same weight distribution, you have to have the same number of code words. And then you need also an efficient algorithm to see, okay, are the code words the same just up to sort of permutation of the entries? So if I were to do this, it would be a very clunky code that would take like a million years to do anything, but my current and former students are clever guys, so they could write a very efficient code. And so they started testing. And this is what led us to the conjecture here. So we had a computer running nonstop for about a half year, testing in dimensions 4 and 5 very, very many cubes. And this leads us to think that flat 4 and flat 5 are 2. And the example that we found in dimension 6 actually came from Q is 5. Yes?
Do you know if the other direction, do you know that if you have isospectrality, then like the worst case scenario must come from this? the biggest, the largest amount of, the largest tuple of elements that are isospectral must come from such a construction.
Ah, so if you have a large collection and they're not necessarily, from integer lattices, right? Then do you know that you get the same thing for integer lattices? And I believe the answer to that is yes.
So it's clear that here you only get commensurate, that your tori have cycles that are commensurate. So that's the integer lattices. And it's clear that if you have incommensurate, then you have less multiplicity, so you have less chance of isospectrality. So it's kind of, heuristically, you would expect that the commensurate case would be the worst case, where you will see the highest amount of, the largest tuples of isospectrality, but the question is if...
No, it's true. So if you have a collection of isospectral, non-isometric flat tori that don't necessarily come from integer ones, and of course, coming from an integer lattice is the same as coming from one with rational points because of scaling. But then there exists the same thing, but from with integer lattices. So if you sort of can't find them this way, it indicates you won't find them at all. So we found them with this handy-dandy code, and then that led us to conjecture, yes, that you won't find them in dimensions 2 and 5, and we have an idea for how to generalize the proof of Schumann to dimension 4 to prove that you can have at most pairs. So that is a work in progress as well. So now we looked at the problem for tori, and I want to now...
Excuse me, how do you check that they are not isometric?
Ah, thank you. Sorry, I forgot to say. Yes, okay, so that's a great question. So to check that they're not isometric, right. So, non-isometry. So if I have lattices, say ai, zn for different values of I, then what we can do is we can build quadratic forms by taking ai times its transpose. And then, so the representation numbers of this quadratic form are basically the same, more or less, as the spectrum of the flat torus. And the flat tori are isospectral if and only if. So the flat tori are isospectral if and only if their Q's are integrally equivalent, which basically means they differ by putting it this way, you sort of eat the O of n part, but you don't eat the GLN Z part, right? So if and only if BTQJ B is QI for a GLN Z B. But knowing the A's and thus the Q's, you have that there's a little theorem that says this. Let lambda min be the smallest eigenvalue of the matrix Q1, which is positive definite, so it's positive. Then if I have such a BTQ1B being equal to Q2, then the columns, so the lengths of the column vectors squared, are less than or equal to the diagonal entries, of Q2 divided by lambda min. So that will tell us that there's actually only finitely many candidates B for a given Q1 and Q2. Because we have this constraint on the norms, and they're integer matrices. So what do? Another computer program. Finitely many B's to check, because finitely many integer matrices will have this upper bounds, because we know the Q's and we know the lambda min, because we know the Q1 and the Q2. So you run this check, and then you see, could we find any B's that satisfy the theorem? No, we couldn't. We're done. They're not isometric.
So that's here isometry or isospectral? This characterization.
Sorry, not isospectral. Isometric. Sorry. Yes. We already got the isospectrality from the weight distribution. Yes, I'm sorry. This was isometric. Because remember, isometric means you have an O of n on one side and a GLN on the other side. But because of this transpose in the definition of the quadratic forms, when you have the O of n element, you do, this thing transpose, you get the identity, so that goes away. But that doesn't kill off the GLNZ side, which is what this term is saying. So they're isometric if and only if the quadratic forms are integrally equivalent, i.e. Sandwich between a GLNZ and its transpose. And then there's only finitely many candidates once you know what those quadratic forms are. So you can calculate it. Okay. Yes. So if it's all right with you, I'd like to leave the realm of flat tori and go back to the very beginning with our question about whether or not we can hear the shape of a drum. So that question was posed by Katz in 1965 or 66. Let's forget. And it was specifically referring to planar domains. Can two planar domains be isospectral and not be the same shape? So let's just change this to polygonal domains. And so we just say the two polygonal domains are congruent if they're the same shape, in the same sense as flat tori. Okay, and now we can define the analog of these, we call them flat choir numbers, because you could imagine that the isospectral, non-isometric objects sing in unison in a little choir. So we could define the same analog for polygonal domains with different numbers of sides. Right? So if I look at triangles, does anyone know what flat triangle is? One by your mathematical sister, Zep. So if two triangular domains are isospectral, they are the same shape. Now, I'll put some dots in the middle. Does anyone know for sure when this goes up? Because we know the answer to Katz's question. One of the people who answered it is is a mutual co-author of some of yours.
9.
So yes?
9. 9,
exactly, very good. So if you look up the famous example, actually their original example isn't the one that you get on Wikipedia though. The turquoise one that comes up on Wikipedia is not their first example. I have to look at their first example because I think their first example has more than 9 sides.
Yes.
But this one came later and it has 9 sides. So, again, what happens in the middle? Yes?
When you define the moduli space of polygonal domains, do you just divide by rotations, or is there another rotation reflections, or is there more symmetry that we need to think about?
No, it's just rigid motions of the plane.
Okay.
Or, you know, in very elementary language, are they the same shape?
No, because for the tori we also had the right hand multiplication by GLMZ,
Oh, right.
which is non-trivial. I wonder if the polygonal domains have some non-trivial, except for the rigid motion.
Just rigid motions of the plane,
Okay.
that's it.
What is the boundary condition?
Yes? Assume a nice one, Dirichlet or Neumann.
You fix the boundary.
Fix the boundary condition, definitely. Yes?
For hyperbolic, before the quadrilateral is bigger than 2. For hyperbolic polygonal domains,
Sure. But I haven't gone into that moduli space, but that's room for exploring. So, yes?
Much sillier question that you maybe addressed this, but the spectrum, do you count things with multiplicity or just the numbers?
We always count multiplicity.
Okay.
So like in my very first example, the 0 eigenvalue was 0, but then all the other ones, we're going to count them twice.
So in all these examples, they're isospectral with multiplicity.
Yes.
Right.
Yes.
Okay. And would the answer be different if it were for...
Good question. Right, so I wanted to kind of stop more or less here, but I'll just share a little anecdote. So when they were proving that there exists these isospectral, not isometric domains, at that point in time, the late 80s, Bouzet constructed isospectral, non-isometric surfaces. And so they knew how to do that. But the idea was, how can we take these surfaces and fold them and then end up with domains that are flat now, that are also going to be isospectral, but then are going to have different shapes. So it's a funny story because the authors who proved this, Carolyn Gordon, David Webb, were married, still are, and Scott Wolford, right? So they had all of these origami shapes in their house because they were trying to build these surfaces, cutting and pasting paper and actually making them. And I asked, did you ever try to do this with 3? And Carolyn said, no, we haven't. Because I'm very curious to know, can you get a triplet? And my student Gustav has tried. It seems challenging. It's tricky, but it's a very basic, cute question. Can you get a triplet? And of course, when is the tipping point? How many sides does the answer change from isospectral guarantees isometry to it does not anymore? So, thank you.
Thank you very much. So, any further questions for Julie? Jean?
So in order to obtain these isospectral polygonal domains, they can all be decomposed in some number of isometric triangles. So if you ask these questions amongst domains that can be decomposed in some number of isometric triangles, do you know what's the minimum number of triangles you need to start getting isospectrality?
So you can also do weird things with them, though. So this method of origami method, let's call it the origami method. You could also do weird things like cut squigglies out of them.
Sure, but I'm specifically asking when you already know that you will only decompose them in some number. I'm taking n to be the number of isometric triangles in which you decompose your domain. Would that be an interesting question to know? From how many of these triangles can you get isospectrality?
I think that could be interesting, yeah.
And is this something that has been...
Because, I mean, we know if you're only using one triangle, right?
Uh-huh.
And we could conjecture, actually, if you're using two triangles, don't you get like a, well, they could be different. So, but isospectral parallelogram are isometric.
Uh-huh.
Isospectral certain trapezoids are also isometric. So you could already start exploring for two triangles. My guess is maybe for two triangles, you won't be able to get isospectral non-isometric.
I guess the reason I'm asking that question is that similarly to how with the tori you wanted to reduce your moduli space to something that was attackable in a specific way, same in this case with the computer programs. The moduli spaces of all polygonal domains with some number of sides can be very large, but those that can be constructed from triangles might be small enough for similar types of approaches you've had to also work again.
Yeah, I mean, although any polygon is determined by is it 2n minus 3? 2n minus 3 quantities. So it's a finite dimensional space.
Tori as well, anyways.
But yeah, no, that's it. That's a cute way, I think, of breaking down the problem and investigating it, is start with things that are constructed with triangles. Because you see, that's what these look like.
So look at the question.
So in these examples, there is a procedure to construct in order to prove the isospectrality, you can construct the new eigenfunction starting from the old one.
Right.
Do you have the same construction in your examples on tori?
Oh, we didn't. I mean, we didn't. We didn't bother with them.
Yeah. Okay, so you know that they are isospectral, but you don't necessarily know how to construct the corresponding eigenfunction.
Well,
functions are simple.
exactly. I mean, for a flat torus, the eigenfunctions are like e to the 2 pi I lattice vector times the vector in Rn. So, but then again, when you know the spectrum, you're only knowing the lengths of the lattice vectors. You're not knowing the actual direction, etc., of the vector. So it's not immediately obvious, like, how to do that or how that works. But I mean, we also didn't really spend. I mean, once you have an example, you know everything about it, right?
You know the degeneracy. Spectral multiplicities. The integer lattices.
Yeah, exactly. I mean, you can always compute a finite quantity, and in dimension 6, things aren't that bad. But it does grow exponentially as the dimension goes higher, which is why hopefully lattice-based encryption is going to save us all from post-quantum computers or quantum computers.
Any further questions for Julie? So we have one there.
Yeah, silly question, but is it obvious that if you don't have the same number of sides of the polygonal, they cannot be isospectral?
That's not obvious, and it's actually for like my example is the Laplace spectrum, and if we just take like Dirichlet boundary condition, there's nothing that says that two isospectral polygonal domains must have the same number of sides. They must have the same perimeter, but they could have different numbers of sides, and so we don't know.
Number of corners does not appear in
the number of corners doesn't appear either. It's this funny combination with the angles at the corners. But yeah, exactly. So the number of corners doesn't appear at all. But if you look at a different related problem, the Steklov problem, then you can say a lot more about the side lengths, number of corners. We have some super experts on the Steklov problem here. So.
If you allow mixed Dirichlet boundary condition, you can have isospectral examples with different number of sides.
I think we have an expert on that in our audience too. Right? we can get lots more isospectral non-isometric examples if you have mixed boundary conditions.
So we have one final question.
Okay, so in those cases where Bn, where flat n is at least 2, it means that you have points in your moduli space that are not determined by the spectrum, right?
Yes.
So you've got this set. Do we know what this set looks like? Is it only dense, or is it finitely many points?
It's not finitely many points, no, because once you get to dimension 4, you have the whole one parameter family. So there's infinitely many examples, because once you have it in dimension 4, then you have the same kind of thing in dimension 5 and higher by just taking a cross product with a circle, right? So, but so if you think of the moduli space of flat tori, and then you give it, a measure, then the set of these isospectral non-isometric things will have measure 0.
Okay, so typically it's...
Yeah, and that's proven by Scott Wolpert in the late 80s, early 90s-ish. Nice paper, by the way.
Fantastic. So let's postpone any further questions to the coffee break, and let's thank Julie.